I taught modal logic for many years, and I used a book that I liked very much, that Hughes and Creswell, and I even used it in its updated version, which I liked better. And then I stopped teaching modal logic for various reasons, partly having to do with university administration, partly having to do with moving to computer science. But I noticed this new book on the blog by Patrick Blackburn on modal logic, wonderful text, and I feel deprived that I never was able to teach out of it because I didn't really learn it. But I just have admired that book so much, as I told Patrick earlier, it actually sits right on my desk next to my computer, so I can check various things that I think I need to know. So anyway, he's going to tell us more things we need to know today. Patrick.
Thank you very much. So, I should say straight away that the word character in this talk does not, alas, refer to the sort of characteristic things like great intellectual skill, great scholarly skill that we have come to know and love in Melvin fitting in his work. More on that later. But it actually is a technical term. It was introduced basically into the study of natural languages, the study of what are called indexical expressions by Camp and Kaplan a long, long, long time ago, even in the 60s. Okay? And that's part of the title of my talk, but the other part of my talk has got the word hybrid logic, and this really does have a lot to do with what Melvin has done. I don't think I can remember a paper of Melvin's that I can point to and say, yeah, that is exactly hybrid logic. But for many, many years, he's been influencing hybrid logics. Maybe the word should be fellow traveler or something here. So I think a lot of people in the modal logic community, hybrid logic community, consider him a sort of inspirational figure, and also somebody whose work in various directions has influenced the way that hybrid logic and modal logic has developed. And we'll see a little bit of that in this talk. Okay. Basically, I don't want to assume that anybody here knows any or cares anything about hybrid logic. I don't really want to assume too much about your knowing much about the way ordinary human languages work when they talk about time. I'm just going to give you a sort of gentle introduction to all that sort of thing to give you the flavor. And only then, in the last part of the talk, am I going to turn to some, well, I was going to say recent work, and this, in one sense it is recent work, but in another sense it's very, very old work, since we're looking back at some of the classical stuff by David Kaplan and Hans Camp, and it's also, in a sense, reviving some work that I did about 20 years ago, which I suddenly discovered at a horrible start when I actually dated it. So the new part of the talk is right at the end, and basically the aim is to point out connections with Melvin's work, expose you to this sort of stuff, and hopefully do so in a way that will keep everybody awake, even though lunch is just down the corridor and the coffee is maybe running out. Here's another man of character, and a very interesting one, one who's been mentioned already. This is Arthur Pryor, I guess probably the most famous logician to come out of New Zealand, with the maybe possible exception of Robert Goldblatt. I'm going to take Arthur Pryor as a starting point for this talk, because I am going to be coming in through natural language and the way time is used in ordinary language. Oh dear, the bottom part of the slides are not going out there. Never mind. I'm not just going in through Arthur Pryor because he got everything right or that I approve of everything he said, but he did do some interesting stuff. As everybody knows, he was the inventor of tense logic. As rather few people seem to know, he was also the inventor of hybrid logic. He was also a big influence on people like Hans Camp. He played a surprisingly large role, and one that still endures, and I'm going to take his work as starting point. He also realized very early on why modal logic is interesting, and let me try just to give the three slogans that are right at the start of the book you mentioned as to why I think modal logic is interesting, and why I think a lot of Amsterdam logicians, up to and including Johan Vambentum, think that modal logic is interesting. Modal languages are simple and yet expressive languages for talking about relational structures. Modal languages provide an internal local perspective on relational structures, And modal languages are not isolated formal systems. And indeed, the only thing I dislike about these systems is that we backpedaled a bit in the book and we wrote relational structures, to be polite, instead of writing what was really in our hearts, which was graphs. Modal languages are good simple language for talking about graphs from the inside, and please don't study them as isolated systems. Relate them to other languages for talking about graphs. Let's just go to the kind of standard definition of a propositional modal language to make sure that we're on the same page. By a modal language, I mean something like this. You've got a collection of propositional symbols. You Boolean close the language. I don't really care what you take as primitive or what you don't. You've got a collection of what you call diamonds and a collection of what you call boxes. A matching box for every diamond, a diamond for every box. Isn't that nice? A diamond for every box. You can just imagine that. The gift-giving possibilities here. Okay? And now, of course, we bring the magic ingredient. We bring in the Crip models. Now, what are Crip models? Well, basically, we've got a set W. So we've got the ghost of the worlds there, of course, the possible worlds. Basically, we've got a non-empty set W, and we've got a collection of, we'll stick to the binary case, binary relations on that world. And these structures are meant to model the things we find interesting. So, for example, we will often think of the elements of W as things like possible worlds or epistemic states, or, as I will be doing today, points of time. We could think of them as intervals of time. We could think of them as preference. We could think of them as nodes in a parse tree. We could think of them as the individuals in this room and their properties, like who is sitting next one to the other. I mean, there is another logic out there called description logic, which you may have heard of, which is essentially a notational variant of hybrid logic, roughly speaking, but with a different history, different approaches, and so on and so forth, but very, very closely related. Okay? Binary relations we find interesting, and evaluation. And then comes the crunch, there comes the crunch, now comes the internality. How do we evaluate formulas inside models there? And the point is, if you really want to understand modal logic, I'm not going to do the dance anymore. If you really want to understand modal logic, think of a modal formula as something like a creature or a little automata. And think of the graph, the Crip model as something out there, and you take this little creature and you put it in the graph somewhere. Now, if it's a little atomic creature, all it's got to do is check whether where he or she is standing, in fact, has the matching form of information. If it's a Boolean one, well, you take the creature apart in the obvious way. But if it's a modal graph, if it's a modal creature, in particular, say it's a diamond creature, the diamond is an instruction for that creature to search to see whether it can make an appropriate transition to find another state where the information will be true. In other words, think of modal formulas as graphs or as little automata or as little creatures. You put them in the graph and they start moving around and exploring. This is not meant to be a wild metaphor. There will come a slightly hand-waving stage. It is actually the key to one of the more interesting characterizations, model theoretically, of what modal languages actually are, namely the Vambentum characterization theorem. But a little more on that later. Let's get a little bit concrete. Arthur Pryor realized this. This was actually before the days of Crip semantics, but Arthur Pryor had a very vivid appreciation of modal logic. And he invented a simple modal language in which he had two diamonds. The F diamond, which looks forward into the future, and just imagine some kind of flow of time. Don't ask too many questions at the moment as to whether time is linear or branching or whatever. Just, you've got some kind of flow of time. Okay? F is your diamond that looks into the future. F phi means at some point in the future. P phi turns around and says at some point in the past. So that's the past, that's the backwards looking diamond. And of course, as I said, every diamond has its box to put it safely away in. So G is the forward looking box at all points in the future. It is going to be the case in the future. And the H looks back into the past. It always has been the case in the past. Okay? And that was basically Pryor's tense logic. It's kind of nice. It really is kind of nice. I mean, and Pryor explored it, one might almost say, with great love. I mean, his book, Past, Present and Future, really is a book written with great passion and appreciation. It deals with philosophical matters, it deals with technical matters. Actually, you'll find there, parenthetically, the first kind of detailed account of what hybrid logic is, which we're not up to yet. He also had a great semantic appreciation for it. I mean, he knew very clearly that, for example, this formula here, FP implies FFP. If I can move it to the future and CP, then I'm guaranteed to be able to hop forward twice in CP. He realized that the validity of that amounted to assuming that time was dense. Between any 2 points, there is a third.
It's the zero paradox.
Very good. He also, interestingly enough, he also realized, though I don't think he had a proof of it, that this language was not strong enough to talk about irreflexivity. He realized that, okay, this is a very fundamental feature of time, no temporal point precedes itself, and he perceived quite clearly that actually his little language wasn't strong enough to see this temporal property. But as I say, I don't think he had a point, but he certainly saw it. Okay? And now let me sort of turn around and start going on the attack of it. Okay? It's nice, but it's not nice enough. Okay? And the ghost at the feast is temporal reference. Pryor's system is not a serious way of modeling time in natural language. Okay? For example, Vincent accidentally squeezed the trigger does not mean, whatever it means, that at some point in the past, Vincent accidentally squeezed the trigger. What it really means is that at some contextually determined point of time in the past, you get the trigger squeezing. Okay? Please also don't focus on my use of the word point. I'm going to be talking about points of time and so on, and I'm fully aware that if you really want to get serious, you want to start using events and intervals as well. But actually that's just a red herring, because the sort of hybrid logics I'm talking about enable you to go there. But points are nice and simple, and the big point is you don't have temporal reference, be it to intervals, be it to points. Okay, that's the killer issue that I'm trying to address, and it's a big issue. Okay, let's move on. That may not seem like such a good example, but now consider this little text. I mean, the importance of temporal reference really comes out when you start considering text. Vincent woke up. Something felt very wrong. Vincent reached under his pillow for his oopsie. Now, we all know exactly how to interpret that. The way you have to interpret that, if you're working in points, is the first sentence establishes something happening at a point in time, or waking up. Then, at the same point of time, because we're talking about points, or if we were in intervals, at an lapping interval, there is the moment of worry. And then, narrative, things move forward slightly and we get the reaching under the pillow for the oopsie. A linguist would basically say that we know this because of the form of the verb, state, verb, and the event verb moves things along a bit, roughly speaking. But the point is there are 3 temporal references. There is a temporal configuration, 2 points the same, and 1 coming after. We don't have a way of dealing with that in a prior style logic. This is a little bit crude, but let me just sort of say as the introduction here, hybrid logic is intended to be a way of fixing these kind of problems. That's first basic take on what hybrid might be.
Or you want them later.
Sorry?
You say that there is no way, but what about a conjunction happened in the past? Then you are saying that they happened at the same time.
I'm sorry, I don't understand.
The conjunction of his waking up as something feeling wrong, is a conjunction
Yes.
happened in the past.
Maybe you'll get the answer to that when I actually consider how I do it in hybrid logic, okay? Because there's a couple of other constraints there, but yeah, let me come to that. Okay? Now, when we're fixing a logic in some sense, when we're adding to a logic, there's different ways we can do it. We can take this little butterfly that is priori intense logic. It's decidable. It's about as close to propositional logic as it's possible to go. I mean, it's propositional logic with 4 innocent little operators. It's decidable. It's happy. I'm talking about the propositional case. We don't want to add temporal reference by sort of bringing on this huge, great machine, dumping it on it, and saying, now we've solved the problem. Okay? We would like to be, in a sense, sensitive and do it nicely. How can we actually do this, since there aren't really any moving parts to fiddle with? Well, there is one part you can fiddle with, and that's the information at the atomic level. Okay? And actually, this was what Arthur Pryor did do, and funnily enough, I'll explain why it's funny enough. He actually did it in past, present, and future, at least for the first time semi-systematically. He basically came up with this idea: treat formulas as terms. Or to be a bit more explicit, make use of certain kinds of formula symbols but enable them to be used as if they were terms, as if they named, as if they picked out something. Okay? And that's it. Let me just give you the detail, and we'll see where this takes us. Okay? Let's hybridize ordinary tense logic. So take the little language of tense logic that I've just given you, and now we're going to add a second sort of atomic symbols, okay, which we'll call nominals, and instead of writing them as P, Q, R, yada, 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 we're going to write them as I, J, K, and L. We call them nominals. That's the only syntactic change. Basically, when we parse a sentence, we come down to the end, we hit an atomic symbol, we've got to say, is it a nominal, is it a variable? We just mix them up in the usual way. That's the only change at the moment. For example, this would be a well-formed expression. You can say in the future I and P, and in the future I and Q, therefore in the future P and Q. And notice that we've mixed the nominals with the ordinary propositional variables. The semantic change is the following. We just insist that in any interpretation, every nominal is true at precisely one time. Okay, so there is a restriction on valuation. Okay, and that's it. Once, okay, we've already got a stronger logic, by the way. Okay, like consider this. This is obviously not a valid formula. If I can look forward into the future and I see R and P true together, and I can also look forward into the future and see R and Q true together, then I can see P and Q true together, which is obviously, I don't need to explain why to this audience, I'm sure, not correct. Okay, but now consider this. If I look forward and I see I and P, and I look forward and I see I and Q, the extra information that they are nominals forces the validity of this. So already we have a stronger logic. And we also have a temptation. And as Oscar Wilde sort of said, whenever there's a temptation, the best thing to do is to fall for it. Okay? So the temptation is, once you have nominals in your language, is to add what we call satisfaction operators. So formulas of the form at I, phi. Think of these as modalities. We've got at subscripted by a nominal, which we stick in front of a formula. I think you pretty much read what it's meant to be just from the way I've described it. The instruction to evaluate this formula is you go to the point named by that nominal, and there must be one, because nominals name are true at precisely one point in every model. Look at that point named I and see if phi is true there or not. Please note, for any formula in any model, any formula of the form at I phi is either true everywhere or false everywhere. And I don't really think I'll be able to make use of this point in the next one. Another way of thinking about them is not so much as satisfaction operators, but for those of you that are used to thinking about first order modal logic, but as rigidification operators. Okay? We're in a sense fixing, we're picking out the value of phi at one particular place in the novel. We're turning that into a value. That becomes very important in certain extensions of this. And now we can fix the obvious. So, in the past, Vincent accidentally squeezed the trigger. Well, in the past there is a point I, and Vincent squeezed the trigger at that point. But maybe this answers your question a bit more. Let's go back to that text. Because the point is, if we wanted to make this text, we wouldn't want it to be just sort of lumping everything together like that. We would probably be wanting to be able to stream in that text and do it bit by bit. Imagine you had a decent parser and you've got some kind of way of building up, say, semantic representation, say, a la Montague, sort of thing that's very, very easy to do. In comes the first sentence, Vincent woke up, yada, yada, yada. We apply our lambdas and, okay, it's a silly representation, but basically we say, okay, this first sentence means in the past, there is a waking up, and it happened at some point I. Okay, in comes the second sentence, okay? Something felt very wrong. So we go to work again, and immediately, well, it's a past tense sentence, so in the past, there's a something feel very wrong time, and it happened at some time J. Ah! How do we tie these together? Like that. We just do the deduction, state sentence, ah, that's demanding inequality. We say at J, I. At the point named by J, I is true. In other words, this is simply a modal way of saying I equals J. And this is the first time we're explicitly saying what is going to be a big theme of this talk, the way that hybrid logic really is something like, hybrid logic is something very, very like first order logic in a certain way, except living down in P space.
Could you use I instead of J in the second formula?
You could say at Ji,
No,
or at
I
ij.
in the P of I and something further down?
You could, I just like, okay.
Yeah.
I like factoring out the two things. These are two separate things. That's something that a parser would spit out automatically, and this is like constraints that would have to be resolved, okay? I think it just more models what would go on, but yes, you could do that. Now, then this one, Vincent reached under his pillow for his oopsie. Okay, there's a k time, but this has to be slightly ahead of time, and so we add this, that at k, you see j in the past, and we've got our configuration, okay?
I hope the Uzi was not meant for Brian Lighter.
I'm sure.
You don't know the story anyway. I'll tell you.
No, okay. In fact, you can do a lot more. I mean, I'm not. Damn it, sorry. Okay. There was another writer, very early writer, on tense called Hans Reichenbach, and he actually systematically tried to explain tenses for all languages in terms of temporal reference. He basically said that basically tenses are basically playing around with 3 points. The point where you're standing, the point where you're speaking, the point where the event you're describing took place, and a funny reference point, which in a sense is the perspective. And a nice way to see this is something like I had seen, which is very nice in hybrid logic. It's sort of saying, in the past there is some point, and before that, the seeing took place. And that seems to be exactly what this tense in English is. Something there and before that. The funny thing is, what I've done here is I've just given basically examples of all Reichenbach's thing, and I just put down here the way that they fit in, the way that they can be done with priori and tense logic and nominals. The weird thing is that Pryor didn't like Reichenbach. He discusses Reichenbach's work in two very, not precisely contemptuous pages, but two very unappreciative pages. He doesn't really say anything very, very contemptful. He just basically says, well, a sentence like, I shall have been going to see John requires more than one reference point. That's pretty much all he says, and so Reichenbach is not good. You basically get the feeling that he thinks there's something fundamentally non-logical about Reichenbach, and there's something right about what he's doing because he's got a logic, which is very, very ironic, since this is in past, present, and the future, which is actually the first place where he's starting to really get systematic about hybrid logic, though not yet using it, and he hasn't spotted it. I mean, it's become a truism practically in the literature that A, Reichenbach and Pryor don't go together, and B, you shouldn't be using modal logic for time anymore because you don't have temporal reference. Both are false. Okay, both are false. Indeed, very false. What's essentially going on is we're getting this analysis here, shifter, brackets, restrictor, and matrix. So a modality which shifts, a restrictor, and a matrix of information. And this seems to be a pattern that repeats in natural language, like, for example, I shall have been going to see John. Well, you just iterate it one more time, and you get Pryor's pattern. It's like that. But now let me try and turn from linguistics to the more logic side. I've promised you that I'm not trying to create a Frankenstein's monster here. I'm sort of trying to create, I started out with a beautiful little butterfly, and, I want to sort of prove that hybrid logic still has its kind of butterfly credentials intact. Okay? What is hybrid logic? I'll tell you what hybrid logic is. Hybrid logic is good old-fashioned modal logic. End of story. And I'll explain why I think it's good old-fashioned modal logic. End of story. Let me start out with a few, not banalities, but a few easy things. Well, for a start, I don't think that either the syntactical feel or the general form of modal logic has been compromised in any way. Okay? We've got sorting on the atomic symbols. We've got some new modalities. Okay? Moreover, these new modalities, the at-Is, are very, very nicely well-behaved modalities. If you look at them, they are normal modal operators. If you can prove phi, you can prove at-I phi for any phi. Or rather, if phi is valid, then so is at-I phi for any choice of I, any choice of formula. Okay? So basically, generalization works for these things. They're self-dual modal operators even, as well as being modal. So not at-I, not phi is the same as at-I, if and only if at-I phi. They're about as nicely behaved as modalities as you could get. Okay? You don't typically pay a computational price for hybridizing. Like if you're dealing with an arbitrary multimodal language over arbitrary classes of models, when you're working with an ordinary modal language, you're p-space complete. Okay? You add the apparatus I told you about, the nominals and the at operators, you're still p-space complete. Sometimes things change, like in the tense logical case, it's actually rather cute. You take pryor and tense logic and then you drop one single nominal into the mix. Boing, just like that. No at operators, just one single nominal, and you go up to x time. Okay? This is actually rather nice. But generally speaking, once you sort of put a bit of structure on the frames, or even if you add a lot more, it's very, very hard to get out of X time unless you start introducing heavier hybrid machinery of the sort that I'm not going to tell you, that I'm not going to talk about today. Basically, you don't pay a computational price normally. And there seems to be this sort of stable point, just like for a lot of tense logics around about X time. Okay? But I want to dig a little bit deeper. Okay. Now, as you're probably all aware, any modal language, and the point I'm just going to make here is that any hybrid language too, can be regarded as a fragment of first-order logic. Why is this? Well, the semantic reason is that these Crip models are simply just relational structures in the ordinary sense. They've got all the information to interpret an obvious first-order language, where we use binary relation symbols for talking about the structure that the modalities see. We use unary relation symbols for talking about the information that the propositional variables see. In black, I've given you what is the normal standard translation. So propositional variables, unary predicates. As I said here, so a diamond move, that's looking for a successor where phi is true. That boils down to there exists a y is a successor state, and we keep on translating. Okay? What about the new stuff I've given? Well, look. Translate the I into nominal, say, or new free variables, depending on what your purposes are. Let's say new free variables. Okay. What about at? It's just substitution. Please observe that this translation is generating always a free variable x. This is carrying substitution by putting in the new constant or variable and saying that that is what the free variable denotes, and that's it. Okay. It's pretty obvious that this translation preserves satisfaction. And now comes the interesting point. Both ordinary modal logic and hybrid logic can be regarded as fragments of first-order logic. Which fragment? And the answer is nice, but we'll take one intermediate slide. There's a very natural concept which has come up in quite a few places. Social sciences, computer science, non-well-founded set theory, many places, called a bisimulation. This is a relation between two graphs, okay? And essentially it means that whenever you have every transition possibility in one graph is matched by a transition possibility in another. We also insist that atomic information matches. To give a really silly example, if this is a 3-point model, and this is a 2-point model, and the arrows are going up, okay? What my silly little modal creature, my modal formula, if I put it in there, and then I, so to speak, blindfold it and take it out and I put it here, although you see, and I put it in the base, although you see that there's 2 successor nodes here, and there's only 1 successor node, our little modal animal doesn't see the difference. All this modal, when here, all it sees is, yes, I can make a transition to, say, a P world, but it can't count. And that's all it sees here. You get more dramatic collapses. For example, you can collapse all the integers to a single reflexive point. A creature in the infinite ones just sees, yes, I can make a transition, yes, I can make another one, and another one, and another one, and of course, could well be looping around here, okay? Now, here comes the nice theorem. This is the Vambentum Theorem. The Vambentum characterization theorem says, look, if you look at the image, of the translations, okay, so you translated modal formulas into first-order formulas, which fragment have you picked up? Up to equivalence, up to logical equivalence, you've picked up that part of first order logic which is invariant for bisimulation. So it's an if and only if. I like this result. I like it because I think it shows that modal syntax isn't really arbitrary. It's a nice, natural, bounded quantification syntax, and it picks out something very, very well. Well, guess what hybrid logic is? Okay? Hybrid logic is merely the bisimulation invariant fragment of first order logic when you've got constants and equality in the language. And bisimulation has to respect these constants. That's it. Exactly. Okay? So to put it another way, I think that this machinery I've given you is not in any sense arbitrary. Indeed, to be honest, I would say in a sense that banning hybrid logic from modal logic would have exactly the same sense as saying, well, we really like this first order logic and we're going to teach it in this university, but no equality symbols. Okay, first order logic with equality, no, that's the work of the devil. Okay, no, only pure first order logic must be thought. It has roughly the same intelligence. Hybrid logic is nowadays, I think, part and parcel of modal logic. It's just there. Okay, and that's what it is, and I think that's a good reason why. It has some nice properties, okay? It has some nice properties, I think, that ordinary modal logic doesn't have, and these properties, some of them concern deduction. First, it's deductively natural. It can define new classes of frames, and it can tie these well together. And in fact, what I'm going to sort of say is that unlike modal logic, maybe I shouldn't really say that, hybrid logic has a decent completeness theorem. Okay? And I use a completeness theorem advisedly. Okay? Orthodox modal inference is hard, or at least it's hard to do in a general way. I'm not disputing that you can come up with a nice proof system, say for Lerb logic, or for S5, or for S4, or for K, or whatever. But a general inference system, now that's hard, and that really is hard. Why is it hard? It's hard because when you are doing modal inference, it's hard to get at the inference behind the scope of the diamond. You're coming down, let's say in some sort of tableau, and you've got the information diamond phi. How do you reach behind that diamond and pull out that phi? It's hard. There is no general mechanism for doing so. Sometimes if your frame conditions allow you to do certain things, things work out nicely. Sometimes they don't. By the way, please note that there is a much stronger logic that we're all familiar with that doesn't even begin to have these kind of problems, namely first order logic. What happens when we're going through a proof and we encounter there exists an x phi? Well, we throw away the existential, we scholemize, and we carry on. Okay? Scholemization, so to speak, getting behind the diamond in a general way. That's what's hard in ordinary modal logic. Here's how you do it in hybrid logic. Suppose you're working with this sort of thing and you're sort of saying, at I can make a diamond transition and see phi. This is the inference we make. You just say, okay, scholemize away. At I diamond j, I can make a transition from I to a world named j, and at j phi holds. And yes, doesn't this look a bit like the sort of thing that Melvin used to write about in a famous book a long, long time ago? Oh yes, it does. It does. It looks like Melvin fitting style labeled deduction. There are differences, but yes. The differences come kind of from the next point. I mean, this is just, you know.
How about a connection to justification logic? That seems to have a similar flavor.
Again, you have to turn to Melvin fitting. Let me just run through this again.
Who's an expert in both?
Pardon me?
Mel fitting. Yes.
That's the only connection.
You're innocent, Mel. You may end up to be the only one. Yes, right.
So, let me just run through that one more time to emphasize how first order we're doing things here. That was our starting point. If we were in first order logic, that is if we ran the standard translation, we would be there. What I've been saying is that to do the deduction here, we introduce the new nominal and we go on like that. Presumably in first order logic we would scholemize away and then split up the conjunction like that. It's an exact parallel. Except this is happening down in a p-space logic, this is happening down in a much, much more powerful logic. Now, this is the interesting point here. Okay, we get a lot more frame definability. Now, as you probably all know, things like reflexivity, symmetry, and transitivity are things you can talk about in an orthodox modal language. All of these things here, like irreflexivity, asymmetry, antisymmetry, trichotomy, and discreteness, are things that probably you cannot talk about. I already mentioned that Pryor realized that you couldn't talk about irreflexivity in ordinary priori intense logic, but just consider this formula. If I is true, then it is not possible to move into the future and see I. You're blocked from making a self-loop. The only way you can guarantee that that is always true at all times is if you're working with an irreflexive frame. So in other words, it defines this quality. And now comes the point, we get a completeness theorem. And I say a completeness theorem because in modal logic it's more general to talk about completeness theorems, plural. The theorem for K, the theorem for S5, the theorem for Loeb, etc. This is more like the first order logic completeness theorem, okay? It basically says this. You make your suitable proof system, of which there are now many, Tableau, Gensen, Hilbert, etc., 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 okay? That's complete for the basic thing. Moreover, any axiomatic extension of that, where you only add as axioms formulas made out of nominals, is automatically complete with the class of models that are defined by that. Think to the first order completeness. You've got the completeness theorem, and of course you just add theorems, and that's called the theory. You generate that. There is only one first order completeness theorem. This is kind of like that, or it's going in that direction. Okay? So hybrid logic is like first order logic. By the way, this isn't restricted down there. All the work happens at the propositional case, but this lifts up to first order. This lifts up to first order hybrid logic, and actually to full hybrid type theory. So we've written a paper very, very recently in which we just took basically communal garden, church, Henkin style type theory, and we put it together in the obvious way with hybrid logic, and it works. In both these cases, this is the little aside which I will probably regret since I'm going to run out of time. The key device here is I mentioned that @I can be thought of as a rigidifier. Until now we only use it with formulas. But here in these extensions we overload I, and we do things like @I alpha, where alpha is an arbitrary type, and that is essentially saying rigidify the value that the type in a higher order setting receives there. And so on and so forth. I'm going to give one more slide to say this. By the way, interpolation pretty much goes through too. You pretty much always got interpolation, but I would have to tell a little bit more than I've got time to here. But interpolation goes through for all these logics too, roughly speaking. Okay. Why does this happen? Now I can't give you it all, but basically it comes down to because we can specify Robinson diagrams. Okay, why? Look, @IP and @I not P. Basically, I've got a way of specifying how atomic information is distributed. @ij, not @ij. Basically, I've got a way of saying which points are identical and which points are not. @I diamond j, if I go to I can make a transition to j. @I not diamond j, if I go to I can't make a transition to j. We can specify the Robinson diagrams. And this is basically it. If you think about a Tableau system and the way it works, you basically crunch things down until you get to atomic or near atomic formula. Basically, if you do the job right, you're going to be spitting out basically the Robinson diagram of a model. Or if you want to do it another way, if you want to do it axiomatically, okay, it boils down to the same thing, except there you go build maximal consistencies. But essentially, to put it another way, you've opened the possibility to Henkin-style completeness proofs. Henkin used constants to prove completeness for full first-order logic. Here, basically, a standard technique is you use nominals, or equivalence classes of nominals, to build models. They are what you build the models out of. And these have the very nice property that all points are named and the axioms just work. It's Henkin. It's straight Henkin, but it's Henkin down in p-space. Okay. What time is it? No! No! It's now. We're back to natural language, we're back to temporal indexicals, I'm afraid. It's now. It's a very useful clock here. I carry it with me always, just in case I forget. Okay. Indexical words in natural language. I've been talking about temporal reference in natural language. There's some other nice indexicals in natural language. I, here, now, yesterday, today, and tomorrow. Kaplan's famous validity. I am here now. Very, very difficult to utter falsely. I mean, I've tried for hours, but I've never yet succeeded. Okay. But it's it's better than counting sheep. You're going to try and utter, I am here now, and do that. Okay. Please note that there is clearly, in some sense here, a new class of validities, or an interesting class of validities, like I am here now, if we wanted to sort of put in the temporal stuff, like yesterday, today, and tomorrow, into the sort of logics I was talking about. There's also a problem with this kind of logic. Now, probably most of you are familiar enough with the way modal axiomatizations work. If you've got phi is valid, a normal rule is a necessitation, like at all possible worlds or at all future times you've got phi. So if phi is valid, then at all future times phi is valid. Whereas, sadly, I am here now, while valid, yay. I cannot legitimately and sadly conclude that I am always going to be here. It's slightly sad, but you know, tempus fugit and all that sort of thing, and we're not going to get away. We're not going to get away with it. This actually, although making some jokes about it, is actually quite a problem. There's been quite a lot of energy expended since the days of Hans Camp about particularly trying to fit this extra layer of inference. We've got the notion of an ordinary logical validity, but now we're trying to add on these contextual validities. How you bolt them onto it without running into the problems that they're not sound with respect to one of your most basic proof rules. I'm trying to do that elegantly. And needless to say, if you've got a problem like this, we should go and ask the men of character. And here we have Hans Camp and David Kaplan, who basically gave some of the ideas, basically invented this sort of thing. Camp gave a very interesting semantics for now. In fact, he gave this semantics for now, when he gave this semantics for now, he invented what is now known as two-dimensional modal logic. His basic idea was, instead of working in models where we evaluate formulas at one time, we work where we evaluate formulas at pairs of times. Okay? At pairs of times. And very roughly speaking, if you look at this thing, the second pair largely lay idle until you encountered a formula of the form now phi, and then its job was you jumped back to the second coordinate and you evaluated there. In a sense, the second coordinate was being used as a memory, as a location for where now was, and now was a jump operator to jump back to this point of time and look at that there. It was a two-dimensional semantic, but it was an extremely weak one, very, very weak. Okay? And in fact, one of Camp's first results was that, in a certain sense, in the propositional cases, now operator was eliminable, though he also showed in the first order case it was not. It spawned a huge industry which is still going strong. In fact, two-dimensional logic a lot is happening there at the moment. Okay? Vlach added a matching then operator. Okay? Segerberg introduced the idea of abstract modalities with no obvious intuitive motivation, which could play with these components. This led to general two-dimensional logic, arrow logic, all sorts of things. It was applied in many ways, Stornacker and dynamic semantics, people like David Chalmers in philosophy of language and philosophy of mind. Now these are all very interesting and fertile fields, but a long way from where we're going to go today, since what I want to do, so to speak, is say, go away. Get to chase away the two-dimensionality. Okay? Maybe only for this, okay, for the temporal stuff. Because the point is, I want to put the temporal reference back into the driving seat. And the intuition is very, very clear. Look, the now operator is essentially a jump operator. It's like an at operator, okay? Guess how I'm going to treat now? Yes, it's going to be a nominal, but a special one. In other words, the models are now going to be your usual temporal models, but with a distinguished point, okay? With a distinguished point which we call now, or the context time, and the special nominal denotes that. So to speak, these are nominals that belong to the signature rather than these kind of like more light things that have been floating around for now, okay? And so we'll have a nominal now, and basically at now will be Hans Camp's now operator. It will jump us to now and evaluate things there. Now, this is not a new idea. There's a paper written by Pryor. In fact, it comes in two versions because there was a mistake in the first version. It's a very, very difficult paper. You can see that Pryor is struggling with Camp's insights and trying to incorporate them. It's a tricky paper, actually. I did use this approach in my PhD thesis. Martin Marks and I published a paper quite a while ago where we were using similar ideas and looking at the actuality operator, but now it's come very center stage, and I'm working with Klaus Ravin-Jørns and a colleague of mine from Denmark. We're looking at these and related logics very closely. Okay? And look, the basic idea is we're going to treat now as a nominal, and what we're going to do is we're going to try and separate out the two kinds of logics. We want the ordinary logical validities, and then, so to speak, the contextual validities, the I am here now. That's going to be demanding completeness in the sense of you want the formulas that are always going to be true at the special distinguished node. So logical validity, as always, is going to be formulas true at all points in the model, and we're going to catch contextual validity, so to speak, by saying, add a bit more, catch the things that are true at the special point. Okay? And indeed, we want to do a little bit more than that. Sorry. The basic lemma is this. We can always eliminate now in favour of a regular nominal. It's very simple. It's not unlike the sort of thing you would do in first order logic. You can take a constant, you eliminate it in terms of a variable. Okay? The upshot of this means, that for logical completeness, your ordinary proof system works. How do we get completeness at the special named point? Basically what we wanted to do, we really believe we could do it just by having one axiom, namely now. The assertion of the now nominal, the single axiom. And this is exactly what happens. If you look at it in terms of tableau, contextual validity boils down to, okay, can you get a closed, okay. Logical validity of phi means, can we assume that there is some point I where phi is false and make a closed tableau? That's logical validity. Contextual validity boils down to, can we falsify I at the special point and called now? As I said, it's a weak two-dimensional space. It's just a little bit more. Getting it into axiomatic form is even cuter. We've got this rule which we call Kamp's rule, in honor of Hans Kamp. Basically, the rule is this: that we take our normal axiomatization and we add one rule. It's if at now phi is provable, then so is phi. But this rule can only be applied once and as the very, very last rule in a derivation. So to speak, you prove all this stuff way down there, and then you cash out an outermost nigh. There's quite a lot built into this rule, and that's complete as well. Okay?
What time is it?
Now.
Can I have 5 minutes? Yeah. Why I like this stuff? Well, there's two reasons I like this stuff. First start, it works again on everything. Okay, all the logics that you would have complete with this, it just works. It bolts onto higher order logic and it bolts onto first order logic. But it also gives you a nice conceptual thing because you can capture yesterday, today, and tomorrow. And you can do it without some of the horrible problems that other approaches have had, like scope problems. Like when people invent yesterday operators, they often find out that where you say John ran John ran yesterday, that neither YP, John ran in the past, or PY, neither scope really works. What we want to do is say things like in the past, yesterday, and Otto dies. Really is going to be the representation. There is some point. It's a yesterday time, that's a restrictor, and there's the matrix. So I'm coming back to the shift and refer strategy. And we want to be able to represent things like, tomorrow, Otto died tomorrow. As in the past, it was tomorrow, and Otto died. We'd like to be able to represent it, and we would like it to be unsatisfiable in any model, because of course, the past is pushing you back, and tomorrow is pushing you forward. Okay? And once again, all we do is we add what things are called character functions. So we're working with these points of, what we do is we bolt context onto the model, now as before, and we insist on having these unbroken stretches of time here, okay? I really do not have enough time. We axiomatize all this, and the real point is that we have this sort of theory. These are things that are logically valid things about tomorrow, and as soon as you utter the word now and go to contextual validity, all these modus ponens fire, and suddenly you get all these new contextual validities coming out. So the now operator is very weak, but has a very rudimentary logic. We can capture it, basically by treating it as a nominal. What's also nice is then, with its help, we can code the effect of all the other things. We've got nice axioms about their logical validities, but once you utter now, this suddenly explodes and you get lots and lots of other contextual properties. So suddenly you really do have this two-level of logic again, okay? Okay, I will not say any more, except there's lots of places we would like to go, and I would just like to finish with, because it's today that's special, it's about Melvin Fitting. I wanted to say happy birthday, though I've discovered this is not really Melvin Fitting's birthday, but maybe this is not really a happy birthday. And it was thanks for everything you've done for logic in general and modal logic in particular. But if I could just finish with a slight Melvin Fitting story. I remember when I first met Melvin Fitting many years ago, it was when he was talking at Licks in Edinburgh, which might have been 91 or 92, I can't quite remember. It was a long time ago. We had Jerry Seligman and me and a couple of others had a small logic reading group there, and we asked someone scared me, Melvin Fitting, if he would care to give a talk to us, and he very graciously did. He gave a lovely talk actually on, we were looking at all his papers to do with three-valued semantics, theories of truth and all this. He gave a very, very lovely talk on this, and he spent quite a lot of time with us. And I remember, because I was already a very, very big fan of his writing, I remember asking him, why are your books so clear? And I've never forgotten his answer. He said his books are so clear because in many ways he is trying to write the kind of books that he would have wanted to read himself. And while I would not begin to try to denigrate or in any way underestimate the many technical things that he has done, the many wonderful contributions he's done in so many areas, there is a part of me, and it's a very stubborn part of me, that still says that actually Melvin Fitting, as an educator, basically by the sheer clarity of his writing and his willingness to explain stuff that other writers might tend not to touch because it's too easy or too obvious, time after time after time you get the feeling that the authors who are willing to really delve in and work on what puzzles them, they are the ones who have the influence. And I think everyone will agree here that I think Melvin's books are some of the most wonderful written in logic, and certainly I would sort of say of my 10 favourite logic books, Melvin is up there with about 6 of them, so that's pretty good going.
Listen, you know that the ancient Greeks had a very distorted sense of time. The ancient Greeks, they referred to their time as the present. You and I know perfectly well it's really the past.
That's true. But the Greeks were wrong about lots of things, weren't they? So.
Yeah, and the time is now for lunch. But I thought we might have 1 or 2, 3 questions, especially if one comes from Mel.
Well, I have a technical question.
Yeah.
You had this rule, if you can prove at now phi, conclude phi, but you could only use the rule once.
Yeah.
If you allow the use more often, do you get nonsense, or is it a coherent logic?
No, it would be, it depends. I mean, you could put on all sorts of stupid ad hoc restrictions on it, okay? Because the point is, if you do that, you're bringing, it's kind of like you've said now, you're bringing something contingent into it. And suddenly if you start using necessitation, you're running the usual risk of you've got a P there, and suddenly you're turning it into necessarily P. But think about it this way. When you start a tableau, you falsify at a point. You invent a new point and you falsify there, okay? And in fact, that's the way it's worked with the tableau. At now, we try to falsify there. This is just, got the rule just by thinking, what is the thing in a Hilbert-style system that's the same? It's kind of like you do all your work, and then at the last point you kind of say, now, and you cash it out there. It's basically a natural deduction rule. It's sort of saying that now implies phi. Oh, but now therefore phi. But you only need that piece of natural deduction once, right at the last step of the proof.
Sergey?
Maybe global remark and kind of suggestion. Trying to put this wonderful story in a bit larger, broader context. When you live in a paradise, or a paradigm, it still probably makes sense to acknowledge the existence of other paradises and paradigms. In particular, viewing model logic as just logic as a tool of studying graphs, maybe a little bit too narrow. Of course, the Patrick never claimed that's the only thing, but with all the sort of energy and expository talents which is poured into his writing, his book, it looks like it shifts a little bit. It creates the universe, which it looks closed, but which is not, actually. But take the Gödel lob logic, or lob logic, we should mention. If you characterizing lob logic as something about transitive reversible founded frames, is a profanity. Because it's about probability. The probability this is how Gödel really came to the whole thing. And, probability doesn't reduce to cryptic frames. It does reduce to graphs. It does reduce to final graphs. It's a different thing. And if you look, it's an existential read-not modality. And if you look at in the modalities as originated in philosophy, also very ancient field, that there are so many different readings and expectations about what modalities could and should do, which are not reducible to cryptic frames.
But on the other hand, there is also here a difference between a first-order perspective and a second-order perspective, because I somewhat blasphemously said that hybrid logic had a decent completeness theorem, which was me essentially saying it's got a Henkin-like first-order completeness theorem. That was the point I was trying to make. Now, you could actually argue that orthodox modal logic has got a very nice completeness theorem, and I'm talking about the Sahlqvist theorem. Okay? And what's interesting about the Sahlqvist theorem, I mean, what's interesting really about Kripke semantics is that when you actually look at Kripke semantics through the eyes of correspondence theory, you see that ordinary modal axioms are essentially second order. You are doing something in second order logic. And sometimes these second order formulas have the more or less miraculous property in some cases, like the transitivity case, that they go from these complex second order things to just being funny ways of writing transitivity. Sometimes they don't, like Loeb, or you get weird things like McKinsey plus Loeb, okay? That is actually, I would sort of say, the deeper mystery of modal logic. And in a sense, how can I put it? I agree totally. And so to speak, I would sort of say that the wilder and more interesting creatures tend to live out in the second order territory. And Loeb clearly does live out in Grigorgic logic and things like that. It lives out in the second order territory. Though, by the way, adding nominals and things also increases the second order power.
I think maybe this would be a good time to stop, except you have no question. You're okay? Okay. So do you want to tell us about lunch? You just...